All right, welcome back. We're going to talk about examples of groups. Last time we gave the definition of a group and some essential properties. Now we want to fill your mind with examples so that you have something to think about when we prove these theorems that we're going to eventually prove. You have some intuition about what's true and what this applies to. So one difficult thing is deciding which groups are going to be the examples that are important. Because there's a lot of different types of groups. I mean, a lot. So which ones do I tell you about? Well, I'm going to focus on the following sort of subsets. So we want to talk about number systems, right? One of the purposes of introducing groups in the first place is to generalize the idea of a number system and its various properties, right? So it's going to be really important that we talk about things like the integers over addition. And these aren't going to be necessarily very deep or insightful groups, but they are important. We're also going to want to study cyclic groups, and I'll define that in another video. They will get their own video, but in the meantime, I just want to say that this can be represented by addition modulo p. So I'll just write down cyclic groups here. This is definitely something we want to cover, and if there's an archetypal example for this, we're definitely going to want a representative from matrix groups and Lie groups. So I'm just going to write down matrix groups. These are a super important class of groups. We're going to want a nice example of a free abelian group. Again, something we'll talk about later, and for that we'll have lattice groups. So just lattices. Lastly, I really want to draw attention to groups whose elements are functions and the operation is composition. And this can look very different in different scenarios, but it comes up again and again and again in different contexts. So with that in mind, we also want to draw attention to automorphism groups. So automorphism groups are going to be really important as we change what they are automorphisms of, right? Is it a set, a group, a ring, etc., etc.? And we're not going to define all those things, but it's going to be something that we want to plant seeds for your understanding later. All right, first off, groups which are common number systems. This is important because it generalizes our normal understanding of numbers. So, for instance, we're going to have the integers under addition. So, this is going to be the set negative k, negative 3, negative 2, negative 1, 0, 1, 2, 3, k, etc., where k goes to sort of infinity within the integers, right? So it's all negative integers, all positive integers, and 0, right? The integers, in short. So if we have m in z, and we have n in z, then m plus n is clearly going to be another integer, right? You can just count n past m, and that will land you on another whole number, if you will, or integer here. So it's closed. For associativity, clearly m plus n plus p is equal to m plus n plus p for all integers m, n, and p, right? You can add 5 plus 3 and then add 1 to it. This is going to be 8 plus 9, or plus 1 is 9, sorry. And of course that's going to be the same as if you wrote 3 plus 1 is 4 plus 5 is also 9. So 9 equals 9. So associativity holds. We're also going to have an identity. That identity is going to be the number 0, right? Because 0 plus any integer m is going to be equal to m. So 0 is our identity element in this group. We're also going to have inverses. So if I have an integer m, m plus negative m, right? M to the left of 0 is going to be equal to 0, our identity. And likewise, negative m plus m is 0. So we have inverses. All right, so it's closed. It satisfies the three group axioms. So the integers under addition are a group. But they're actually more than just a group. They're an abelian group, because m plus n is equal to n plus m for any m and n in the integers, right? Doesn't matter which way you add two numbers, the result is going to be the same. So this is going to be our great canonical example of an abelian group, right? Or at least one of them. Now we can do the same thing with the real numbers, right? If we have two real numbers a and b, their sum is going to be another real number. You can think of this as decimal expansions. Maybe it's not the best way to think about real numbers, but it works for our purposes right now. So that if we have like 1.123 blah blah blah, and b is equal to 0.567, etc., that we could just add decimal by decimal place. And at least in principle, it should make sense that we can add any two real numbers, and it's going to give us another real number. So the real numbers are closed under addition. Likewise, a plus b plus c is equal to a plus b plus c, right, where we move the parentheses for any a, b, and c in the real numbers. This should be fairly obvious to you. Once again, our additive identity is going to be the number 0, and we're going to have inverses, and the inverse is just going to be the negative of that number. So once again, the real numbers are a group with respect to addition. Likewise, you could do the same thing with the complex numbers, and so on. So that they all form additive or abelian groups under addition. Likewise, we can consider just the even integers, which we would call 2z. So we have -4, -2, 0, 2, 4, and this is of course under addition again. If you add two even numbers, you're going to get another even number, so it's closed. Because the integers have associativity, the even integers are also associative under addition. 0 is still in the even integers, and we have our negatives still, 2 and -2, 4 and -4, so we have inverses. Now it's worth mentioning at this point that the odd integers are not going to form an additive group. So a mod p is going to be equal to the remainder when you divide a by p, if there is a remainder. Obviously, a and p are going to be integers here. P specifically is going to be a positive integer. A is congruent to b, and then in parentheses write mod p, if a and b have the same remainder when you divide them by p. For instance, 3 goes into 5 once with a remainder of 2, so that 5 mod 3 is equal to 2. Well, we also have that the number 8 mod 3 is going to go into that twice, 6, right, with a remainder of 2. Alright, so if 5 mod 3 and 8 mod 3 are equal, then we would say that 5 is congruent to 8, in parentheses, mod 3. And so you get how this goes. Now it's actually going to be true that this congruence here is an equivalence relation on the integers. In other words, a is always congruent to a mod p. If a is congruent to b, then b is congruent to a mod p. And if A is congruent to B and B is congruent to C, this is going to imply that A is congruent to C mod P. And these are fairly easy to show. I'll leave it to you to do that. Obviously a number has the same remainder mod P as itself. So these two require just an elementary proof, but nothing you can't handle. And of course, this is all built on the idea of the Euclidean division algorithm, right? So that if P is a number strictly less than M, then you can always write M is equal to P times Q plus R, right? For some integer Q and some integer R, such that 0 is less than or equal to R is strictly less than P. I'm not going to give a proof of this, you should have seen this before, but this is just basically the idea behind long division, right? It's called the division algorithm. So one way to visualize this set is as 0, 1, 2, all the way up to P, where we can add any two elements here, and then if it goes beyond P, we count how many times it goes beyond P, and then start from the left again, right? This is what it means modulo P. So that if we have, say, P equals 5, then our set is going to be 0, 1, 2, 3, 4, and then we're not going to have 5 because 5 is congruent to 0 mod P, right? They have the same remainder. 5 goes into 0 times exactly, and 5 goes into 5 1 time exactly. They have the same remainder. So then it's easy to see how we define addition on this, right? Again, we just do normal addition, but then if it goes outside that, we just, instead of going to 5 here, we go back to 0 and keep counting. And that's how addition modulo P is going to be defined. And this set, in fact, this group is going to be called Z sub 5, or in general, Z sub P, where you could put a little plus sign with a circle to denote that this is addition modulo P, right? It's a group. So for any A and B, we'll use this symbol to denote A plus B mod P. Well, how do we know it's a group? Well, to look at the example of Z5, no matter what number you pick here, what two numbers, whatever they add to, you can take the remainder by the division algorithm, and it's gonna give you something which is in here. So clearly it's closed. Now the reason it's going to be associative is just because addition is associative. Likewise, we're going to have an identity element 0, right? And inverses are going to be a little weird because you're thinking, well, we don't have the negative numbers, how could we have inverses? Well, the inverses are going to be different now. Well, the inverse, by definition, right, is just whatever number A inverse, or usually in additive notation it's written negative A, gives you your identity, 0. Well, in this case, there's still such an element, right? 3, if you add 2 to it, gives you 0, and 2, if you add 3 to it, gives you 0. That means 2 and 3 are inverses of each other now in modular arithmetic. Likewise, 4 and 1 are going to be inverses, mod P, and 0 is going to be its own inverse, as is always the case with the identity element. Alright, so addition modulo P is going to be our archetypal example of a cyclic group, and we'll define that a little bit more later. Now, what's later going to be our archetypal example for a free abelian group is we want to think of transformations, and especially translations, in the plane. so that we can form lattices. Let me show you what I mean by a lattice. So that if we have our normal two-dimensional plane, right, this is our x-axis, this is our y-axis, and then why don't we define a function, let's call it sigma, where sigma of xy is equal to x plus 1y. That means wherever you are, let's go exactly 1 to the right. And then let's define a second function, tau, which is going to be defined by tau of xy is equal to x y plus 1. So that wherever you are, tau is going to move you exactly 1 unit up. So we can think of this as tau, this as sigma. Now, repeated application of these two functions is going to get you, for any given point, which we're going to assume is an integer point, right? So we have integer coordinates x and y. X, y are integers. Then what's this going to do? Well, it's going to produce for us a lattice of points, right, that we can achieve by some combination of tau and sigma applying to our location. We're going to denote all possible combinations of these two mappings, these two translations, if you will, as tau and sigma in angle brackets. And this is later going to signify a free abelian group generated by tau and sigma. All right, think in terms of all possible combinations so that we have tau plus tau is going to be a repeated application of tau. And we'll just denote that 2 tau for convenience. There's not actually a second operation of multiplication going on here. It's just that we can think of repeated addition as multiplication, just like you would learn in elementary school arithmetic. So that we have tau done twice can be thought of as 2 tau. Tau done n times can be thought of as n tau. Likewise, sigma applied m times can be thought of as m times sigma. At least that's how we're going to write that. And of course, we can imagine taking the opposite mapping, right? So that if we take the inverse translation, if you will, so that sigma has sigma inverse, right? And tau has tau inverse. And we can think of we could think of negative n tau, meaning take tau inverse n times, and negative m sigma, meaning take negative or the inverse of sigma m times. And what will you get? And then we can start thinking about, instead of just going in one direction some number of times, we can think about combinations of the two, right? So we can think about taking tau, then sigma, then tau again, then sigma again, then sigma inverse, then tau inverse, then tau, then sigma inverse, and etc. And we can think about all possible combinations, which is going to give us this whole lattice, right, given just one starting point. And so we think of this as all sort of integer combinations of sigma and tau. And the whole reason we can do this is because applying tau and sigma is equal to applying sigma and then tau, right? If we move right and then up, that's the same as moving up and then right. That means that this is an additive group. It is an abelian group, a commutative group. So we have a commutative operation here of translation. All right, it should be fairly obvious that it's associative, because if you were to say take tau plus sigma plus tau, just for an example, this is going to give you a diagonal movement, and this is going to give you a vertical movement. And if you go vertical then diagonal, this is going to be the same, of course, as if you were to take tau plus sigma plus tau, where this is a diagonal movement, and this is a vertical movement. All this is saying is that forming a parallelogram. And it doesn't matter if we go this way and then this way, or this way and then this way, we're going to end at the same point. And that is the geometric sort of visualization of the associative property here. Likewise, you have an identity, which is just not translating at all, right? It's going to be 0 tau plus 0 sigma. And inverses, of course, we have moving in the opposite direction. All right, I'd like to talk about the automorphism group, only gently. So suppose we have a set, and I want to consider all possible mappings, specifically bijections, right? So one-to-one onto mappings from this set to itself. Well, there's only two elements, so it's not going to be too complicated. There's only two options, right? We can either map A to A and B to B, or we can map A to B and B to A. So let's call F the mapping that takes AB to AB, and let's call G the map which takes AB to BA. All right, so now what we'll notice is that these two mappings can be considered elements, and then we can use function composition as our binary operation. So what is F composed with G? Well, it's going to be evaluating G first and then F. And this is going to be the action of just G, because F is just the identity mapping, right? It maps A to A and B to B. Likewise, G composed with F is going to be equal to, once again, G, because doing the identity map first and then doing G is just going to give you G. So as I said, it's the identity map, and so that if we take function composition as our binary operation, then F qualifies as an identity element. Likewise, there's no set of compositions of these two functions which is going to give you something other than one of these two functions, right? In fact, you only have four possibilities for your products. There's going to be F composed with G, which we're saying is G, G composed with F, which I'm saying is G, F composed with F, which is just going to be equal to F, the identity, and G composed with G, right, which is going to flip the elements twice, so A goes to B, and then B goes back to A, and B goes to A, and then A goes back to B. So it's going to end up exactly what it was to begin with, so that that's equal to F, the identity. Now this is a very, very simple group, but it is a group. And we have inverses, right? So F is its own inverse, and G is its own inverse in this case. We obviously have associativity, and even we have commutativity in this case. Now, if we were to generalize this to just all bijections between any set and itself, what you're going to get is the automorphism group on a set. The set of all mappings, right? So with sets, this is usually called the symmetric group, and we'll talk more about that later. But in other contexts, like for instance, what if your set is itself a group? So the set of all bijections which preserve a binary operation from a group to itself. This is something we'll come back to later, but in a more general context, we can just refer to it as the automorphism group of a set X or a group G, or etc., etc. All right, for the last really good example here, I want to talk about matrix groups. And specifically, I want to talk about sort of the all-encompassing matrix group called the general linear group. So first, I have to define matrix multiplication for you, since I'm not assuming you're familiar with that. So suppose we have two 2x2 matrices. We'll label the entries A11, A12, A21, A22. And then we're going to take a second matrix, B11, B12, B21, and B22. And the way we're going to multiply them is the following. We're going to want to get a new 2 by 2 matrix, just like these. So we're going to take the product of these two entries, so A11 times B11, and then we're going to go down here while going over here. So plus, and then this product, A12, B21. So it's this row with this column, right? Row, column, row, column. That's important. Okay, so then the second entry, we're going to use this same top row, but then use this column instead. So this is going to be A11, B12 plus A12, B22. Likewise, our third entry is going to use this bottom row and this column right here. So A21, B11 plus A22 times B21. And then our last entry is going to be this row with this column. So A21, B12 plus A22, B22. This looks complicated at first, but really it's not that bad. Alright, so what we're going to notice here is that if these are integers or real numbers or complex numbers even, then what we're going to end up with is a matrix, right, a second matrix, which also has entries which are respectively either integers or real numbers or complex numbers, right? This operation is going to be closed. Likewise, it's going to be associative. If you have three matrices, A, B, and C, of the same size, we're going to assume that they're square matrices here, then A times B times C is going to be equal to A times B times C. Now I told you the operation, but I haven't told you the set that the binary operation is going to be defined on. So first I want to talk about the determinant of a square matrix. So the determinant of a 2 by 2 matrix is defined to be, the determinant is equal to A11, so this diagonal, times A22, so the product, minus the product on this diagonal, minus A21 times A12. That's just how we define the determinant of a 2 by 2 matrix. Alright, to make a very long story very short, we want this determinant, this number right here, to be non-zero. And the reason for that is that if we call this matrix A, that if its determinant is non-zero, then we can show that there exists an inverse matrix, by which we mean another 2 by 2 matrix, which if you multiply this inverse by A, you will get the identity matrix, which for 2 by 2 matrices is this matrix. And for larger groups, it's going to be just the matrix with ones on the diagonal and zeros everywhere else. And likewise, if such a matrix exists, A times A inverse is also equal to the identity. And we'll sometimes write the identity as just this one with a double bar. Moreover, there's some cute properties associated with this determinant operation, which is that if you have the determinant of a product of two matrices, it's going to be equal to the determinant of A times the determinant of B. So this is all a bunch of linear algebra, so I expect you already know this or can find this out on your own. This is not really central to what we're talking about. But what's important is this. We want the determinant to be non-zero because we have those inverse elements, but also because if we take the product of two matrices, we'll obviously get another matrix, But the determinant is equal to the product of the individual determinants. That means if A has non-zero determinant and B has non-zero determinant, then their product is going to be non-zero, so that the determinant of the product matrix is also non-zero. And thus the product matrix, A times B, it also has an inverse matrix, right? So this is exactly what we need for our set of matrices here to be a group. All right, so if we take, in set builder notation, the set of all 2 by 2 matrices, so we'll go M in, and we'll just use real valued matrices as an example, but it could be complex valued. So you could have a complex number, a complex number, a complex number, a complex number. But just for kicks here, we're going to say this is R 2 by 2. So real 2 by 2 matrices, and then such that M is invertible. Equivalently, so if and only if you like, determinant of M is not 0. So if we take this set of matrices, all 2 by 2 real valued matrices such that the determinant is non-zero, this is going to give us a group for precisely the reason I just told you, that it's going to be closed under that operation of matrix multiplication because their determinants have to be non-zero, so the determinant of the product matrix is non-zero. And this is a very, very special group, and it's called the general linear group, in this case of 2R. 2 is the dimension, so if we have a 2 by 2 matrix, right, these are square matrices we're interested in, we could have an n by n matrix, and it's going to be sort of the same story. So n and R is whatever the coefficients are. So n, GL of n z would be, these numbers are integers, GL of n r, they're real numbers, GL of n c would be if we had complex entries, etc., etc. And this is called the general linear group, and it has a lot of interesting other groups that are associated with it, which we're going to see at a later time. All right, so those are our great examples of groups. They should carry us pretty far. We'll probably see some other groups along the way, but those are going to be some real solid ones which I want you to keep in your mind whenever we prove results about groups. How does this apply to the matrix group? Or how does this apply to the symmetric group or the automorphism group, right? Etc., etc. And just as a little bonus thing, I wanted to say that the group I introduced in the first video as a motivation, the group of symmetries of the equilateral triangle in the plane, that's going to be called the dihedral group. So the dihedral group of n, or d sub n, is going to be the set of all symmetries of a regular n-gon in the plane. That's just a little bit of a side note. Alright, so that's an introduction to a few really important groups and classes of groups that we're going to see over and over again in our study of group theory.